This is SpaceTime, Series 19, Episode 82, for broadcast on the 18th of November 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, new clues about mysterious fast radio bursts. The power of the Force appears to be the same across the cosmos after all. And a funnel on Mars which could be a great place to look for life on the red planet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected a powerful blast of gamma-ray energy coming from a mysterious event known as a fast radio burst. The findings, reported in the astrophysical journal Letters, claims the gamma-ray event delivered 1 billion times more energy in gamma rays than in radio waves, thereby rivaling the supernova death of stars in their explosive power. The discovery represents the first confirmed finding of a non-radio emission coming from a fast radio burst. The new link drastically raises the stakes for models of fast radio bursts and is expected to further energize efforts to chase down and eventually identify the long-lived counterparts to fast radio bursts using gamma-ray, X-ray, optical and, of course, radio telescopes. Fast radio bursts, or FRBs, were first discovered in 2007, and in the years since, radio astronomers have detected several dozen such events. Although they only last mere milliseconds in any single frequency, the great distances from Earth and large quantities of intervening plasma delay their arrival at lower frequencies, effectively spreading the signal out over a second or more and yielding a distinctive downward swooping whistle across the typical radio receiver band. One of the study's authors, Professor Derek Fox from Penn State University, says the discovery revolutionizes science's picture of fast radio bursts, some of which it would now apparently seem can manifest themselves as both a whistle and a bang. The radio whistle can be detected by ground-based radio telescopes, while the gamma-ray bang can be picked up by high-energy satellites like NASA's Swift Space Telescope. The rate and distance estimates for fast radio bursts suggest that, whatever they are, they're a relatively common phenomenon, probably occurring somewhere across the universe more than 2,000 times a day. The first efforts to identify fast radio burst counterparts began shortly after their discovery, but they've all come up empty until now. The authors detected the bright gamma-ray emissions originating from fast radio burst FRB 131104, named after the date on which it occurred, November 4th, 2013. Discovery of the gamma-ray bang from FRB 131104, the first confirmed non-radio counterpart to any fast radio burst, was made possible by NASA's Earth-orbiting Swift satellite, which was observing that exact part of the sky where FRB 131104 occurred, just as the burst was detected by the Parkes radio telescope. Although theorists had anticipated that FRBs might be accompanied by gamma rays, the gamma-ray emission seen from FRB 131104 was surprisingly long-lasting and bright. The duration of the gamma-ray emission at 2 to 6 minutes is many times the millisecond duration of the radio emission. And the gamma-ray emission from FRB 131104 also outshines its radio emissions by more than 1 billion times, dramatically raising estimates for the burst's energy requirements and suggesting severe consequences for the burst's surroundings and host galaxy. At the moment, there are 2 models for gamma-ray emissions from fast radio bursts. One involves magnetic flare events from magnetars, highly magnetized neutron stars, the dense remains of collapsed stars much bigger than the Sun. The other involves the catastrophic merger of 2 neutron stars colliding to form a black hole. However, the energy release seen from this event is actually quite challenging for the magnetar model, unless the burst is relatively nearby. And the long timescale for the gamma-ray emission, while unexpected in both models, might just be possible in a neutron star merger event. That's if the merge is being observed side-on in an off-axis scenario. The thing is, the energy and timescale of these gamma ray emissions associated with FRBs are actually much better suited for some types of supernova explosions, or for that matter, some supermassive black hole accretion events. The problem is none of the existing models predicted a fast radio burst would occur in either of these two cases, which in reality tells you how little we really know about what fast radio bursts are likely to be. The bright gamma ray emissions from FRB 131104 suggests that the burst, and others like it, might be accompanied by long-lived X-ray, optical and radio emissions. Such counterparts are often seen in the wake of comparable energetic cosmic explosions, including both stellar-scale cataclysms, such as supernovae, magnetar flares and gamma-ray bursts, and as episodic or continuous accretion activity in supermassive black holes that commonly lurk at the centres of galaxies. The swift X-ray and optical observations were carried out 2 days after FRB 131104 thanks to prompt analysis by radio astronomers, who at the time weren't aware of a possible gamma-ray counterpart. It was also helped by a nimble response from the Swift mission operating team headquartered at Penn State. In spite of this relatively well-coordinated response, no long-lived X-ray, ultraviolet or optical counterpart was seen. The authors are now obviously searching for more fast radio burst counterparts in the hope of narrowing down the most likely progenitor event and eventually finally revealing the sources responsible for these ubiquitous and mysterious bursts. A new study indicates that the strength of the electromagnetic force appears to be the same across the cosmos after all. The findings, reported in the monthly notices of the Royal Astronomical Society, contradict earlier studies which appear to show a difference in the strength of the electromagnetic force in different parts of the universe. The study's lead author, Serdan Kotos from Swinburne University in Melbourne, reached his conclusion by undertaking the most accurate measurement yet of the fine structure constant in the light coming from a distant quasar, which was shining through a foreground galaxy some 8 billion light-years away. In physics, the fine structure constant, which is commonly denoted by the Greek letter alpha, is a fundamental physical constraint characterizing the strength of the electromagnetic interaction between elementary charged particles. Broadly speaking, the fine structure constant is 1/137. You can put maybe a dozen smaller numbers behind it. Quasars are the brightest objects in the universe. They're actually powerful beams of energy which can be seen shining across the cosmos. They're generated by material being crushed together and torn apart at the subatomic level in the accretion disks of supermassive black holes. On its journey towards the Earth, some of the quasar's light was absorbed by gas in the foreground galaxy, allowing the authors to obtain a detailed spectrum telling them just how strong the electromagnetism is in this galaxy. And because the quasar selected was one of the brightest known, the authors were able to make the most precise measurements so far of the fine structure constant. The authors found the strength of electromagnetism in this galaxy to be just the same as what it is here on Earth. According to the standard model of particle physics, the strength of electromagnetism, one of the four fundamental forces of nature, should be constant throughout the cosmos. However, in 2011, Professor John Webb from the University of New South Wales reported in the journal Physical Review Letters that the strength of electromagnetism may change depending on exactly where in the universe you are. Webb and colleagues reached their conclusion after examining the spectra of light from different quasars, which was shining through some 300 galaxies up to 12 billion light-years away, a time when the universe was just a fraction of its current age. Webb's team used both the 10-metre Keck telescope in Hawaii and the European Southern Observatory's VLT, or Very Large Telescope, in Chile's Atacama Desert to examine the ancient light coming from these quasars in order to detect any changes in electromagnetism. What they found was that the fine structure constant appeared to vary across the universe. It appeared to be getting stronger in one direction and weaker in the other, meaning the universe appears to be dipolar. If correct, this discovery would have had profound implications for our understanding of space and time. That's because the fine structure constant determines the strength of the electromagnetic interaction which keeps electrons attached to the nucleus of an atom. In fact, it determines almost everything about our everyday world, including the light we receive from the sun, how we see that light, how sound travels through air, even the size of atoms and how they interact. But no one knows why electromagnetism has the strength it has, and whether it should be constant across the universe, or whether it should be varied. Or for that matter, we don't even know why it's the way it is. If the fine structure constant was different in different parts of the universe, then different laws of physics would mean different properties for chemicals and even biology. You see, a 4% change in the fine structure constant would mean differences in the production of elements which would affect how stars burn, changing the production of heavy elements such as carbon, which of course is needed for life. If correct, the findings may have helped explain why the laws of physics seem to be so finely tuned for the existence of life on Earth, but perhaps not so finely tuned for life to exist in other parts of the universe. In fact, a different strength for electromagnetism in other parts of the universe would have prevented the formation of life as we know it. However, Webb's research was limited by the accuracy of the spectrographs they were using to measure the fine structure constant. To overcome this problem, Kotis combined observations from the VLT with a highly advanced spectrograph on a smaller 3.6 metre telescope at the same observatory. Kotis says discovering that electromagnetism does appear to be constant over half the age of the universe simply deepens the mystery of why it's so.
Electromagnetic force is very important because it's one of the four forces that governs our universe. So only those four forces actually exist, and most of the things that we actually sense as human beings is related to this electromagnetic force. You mentioned the previous results from John Webb and his collaborators showing that there is different electromagnetic force across the universe in different parts of the universe. Yes, that was their result. However, there are regions in the space where electromagnetic force should be the same as here on Earth. And actually in this work, we were probing electromagnetic force in some of those regions where it should be similar to here on Earth. Other problem is that in John Webb's and Julian King's work, they used spectra that was calibrated in a simple way. However, in our work, we tried to do more advanced calibration of our spectra. And by doing that more advanced calibration of that spectra, we realized that there are some other works realized actually that due to some problems in that calibration, there are some problems in those previous measurements. There are some possible problems. And we tried to account for those problems by using additional telescope and spectrograph and additional spectra from another telescope to actually put the right numbers on our ruler with which we measure this fine structure constant.
And when you did this more precise measurement of the fine structure constant, what did you find?
We found that it's similar as here on Earth. But as I pointed out already, our measurements is also consistent with the measurements of Webb et al. And King et al. From a couple of years ago.
The importance of this is really quite profound, isn't it? If the fine structure constant is just a little bit different, elements wouldn't be the way they are now. Life couldn't exist. It's quite an important measurement. It's an important study.
Yes. So if fine structure constant was just 4% different than it is here on Earth, stars, for example, wouldn't be able to fuse carbon. So to produce carbon, and carbon is the main element in living beings, as we know. However, our measurements are probing the differences in strength of electromagnetism on much smaller scales. So we measure in parts per million scales instead of percentage scales that could affect living beings.
So for now, the value of alpha remains 1 over 137?
Yes.
For now.
With a little bit more digits.
Oh,
so we are probing it, as I said, with more digits.
Yes, you're looking at millions.
It still seems the same as it is, but we really need to focus and to measure it from probably even larger telescopes than we have now. By doing that, we could see if it is really constant.
So take me through the process that's involved here. There was this quasar, it was shining its light through a galaxy.
So we use very precise, high-resolution spectrographs, so we can disperse and see the rainbow of light in many, many small details. And then we look at the specific wavelengths where absorption features should be. So absorption in that rainbow should be at specific position. However, if it is slightly different and there is pattern of that difference between what we expect from looking at the spectrum of the same gas here on Earth and there in the outskirt of that galaxy through which quasar light is coming, if there is a difference, that should be due to different electromagnetic force in that cloud.
And there's all sorts of things you've got to adjust in that measurement too, isn't there? Simply because of the distance that this quasar and the galaxy is from the Earth.
Yeah, there is redshift, for example. So as we know, the universe is expanding. So that galaxy is going away from us, and therefore that light is, all of that spectrum is shifted towards red. So we actually see that pattern of absorption lines at different position than it actually is. So we need to adjust for that redshift before we can actually measure the pattern of that absorption and whether it is different from the one that we see here on Earth.
And then you compare it to the one on Earth and let you know whether or not there's been a change in the strength between the photon and the electron, and whether or not that's changed. That's different from here and there.
Yes. Also, there is one problem that was found a couple of years ago. So to make these precise measurements, we need to know actually the right ruler for the wavelength, so where those lines actually rest, okay?
Yep.
So if we don't know it precisely, and what has been found that we don't really know it, and we don't have a really good ruler for that, we need to use other method to actually figure out that ruler. And in this work, we used another telescope to actually figure out the more precise ruler.
This was the 3.6 meter ESO telescope.
Yes. We used that 3.6 meter telescope, has actually better spectrograph, which actually gives us that ruler.
Because previously you were using the 8.2 meter VLT Very Large Telescope. That was the same telescope used by Webb, who was also using the Keck telescope in Hawaii as well.
So we have used both of those. So the size of the telescope is actually giving us how much light we can get from those distant objects. However, spectrograph, we use spectrograph to give some meaning, actually, that ruler that I was talking about, to the spectrograph. So on this smaller telescope, we had a good ruler. However, we were collecting light from the big telescope. And by using both of them, we've put the good ruler onto the light from the big telescope, which gave us more light. And then we were able to measure it precisely as well as accurately.
So really what you guys have done is you've made the most precise measurement yet of the fine structure constant in the distant universe.
Yes. We made the most precise measurement.
That's one measurement. You're going to want to make more, I take it, to look at different parts of the sky and see if it comes out the same.
Yes, certainly. That's really important, as I already said. However, measurements with this precision that we made now are probably impossible to make now at the moment, because this specific quasar that we used is very bright, and because it's so bright, it was observed a lot of times. And because of that, we had a lot of exposures of that same object, and we used all of that exposures to gain this high precision. That was also the reason why we were able to have this spectrum from another telescope, from this smaller telescope. We tried to observe other objects with this smaller telescope. We wouldn't be able to collect enough light to do so. However, next year, new spectrograph is coming online on this 8.2 meter telescope, on very large telescope, which will be also accurate as this one on the ESO 3.6 meter telescope. And with that spectrograph, we will be able to use similar method as we used on this to actually obtain very precise measurements.
From a larger number of candidate quasars, I take it, and consequently galaxies between us and them.
Yes. However, there is still a problem because all other objects, all other quasars from which we can measure, cannot get such precise measurements as we got from this one, because this is the brightest quasar on the southern sky above, particular redshift where we can actually measure this. So if we do it on another quasar, we wouldn't get so precise measurements. So to get more precise measurement, we would actually need to go to even larger telescopes, and they are still being built and probably won't be built in another 10 years or so.
So that's like the giant Magellan telescope and the extremely large telescope.
Yes, telescopes like that.
They're the 30-meter class or something they're being called.
Yeah, 30, 40-meter class telescopes, yeah.
That's Serdan Kotos from the Swinburne University of Technology and Supercomputing in Melbourne. A strangely shaped depression on Mars may well be a new place to look for signs of life on the red planet. A report in the journal Icarus claims the depression was probably formed by a volcano beneath a glacier, and it could have been a warm, chemically rich environment well suited for microbial life. The study's lead author, Joseph Levy from the University of Texas in Austin, says his team were drawn to the site because it looked like it could host water, heat and nutrients, some of the key ingredients needed for life as we know it. The depression is inside a crater, perched on the rim of the Hellas Basin on Mars and surrounded by ancient glacial deposits. It first caught Levy's attention back in 2009 when he noticed crack-like features on pictures of depressions taken by NASA's Mars Reconnaissance Orbiter spacecraft. The depressions look similar to ice cauldrons on Earth, formations found in Iceland and Greenland made by volcanoes erupting under an ice sheet. Another depression in the Galaxis Fossae region of Mars has a similar appearance. Levy says these landforms caught his eye because they were weird-looking. Both were concentrically fractured, so they sort of look like bullseyes, and that can be a very diagnostic pattern seen in Earth materials. But it wasn't until this year that he and his research team were able to more thoroughly analyse these depressions. They used stereoscopic images to investigate whether the depressions were made by underground volcanic activity that melted away the surface ice, or whether they were made by an impact from an asteroid. The authors used pairs of high-resolution images to create digital elevation models of the depressions that enabled in-depth analysis of their shape and structure in 3 dimensions. The team were able to measure not just their shape and appearance, but also exactly how much material was lost from the depressions. That 3-dimensional view allowed them to determine whether the depression was caused by volcanic activity or by an impact event. The analysis revealed that both depressions shared an unusual funnel shape with a broad perimeter that gradually narrowed in depth. That surprised Levy and raised the possibility of it being caused by melting concentrated in the centre that removed ice and allowed material to pour in from the sides. If it was an impact crater, it would have started with a much smaller crater in the past, and by sublimating away ice, it would have expanded the apparent size of the crater. After testing formation scenarios for the 2 depressions, researchers found they probably formed in different ways. The debris spread around the Galaxis Fossae depression suggested it was most likely the result of an impact. But the known volcanic history of the area still doesn't rule out a volcanic origin. In contrast, the Hellas depression has many signs of volcanic origins. It lacks the surrounding debris of an impact, and it has a fracture pattern normally associated with concentrated removal of ice by melting or sublimation. The interaction of lava and ice to form a depression would be an exciting find because it would create an environment with liquid water and chemical nutrients, both ingredients required for life on Earth. Levy says the Hellas depression and to a lesser extent the Galaxis Fossae depression should both be kept in mind when looking for habitats potentially conducive to life on the red planet Mars. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.